cheapest to add. Then again we add whatever, then we grow this, and then we want to add another vertex, then we grow that, and then we want to add another vertex. So this seems okay. Is there a problem? So am I audible? Can you see this screen also?
Yes, sir.
Yes, sir, you're
Yes,
audible
sir.
and it's visible.
Okay. So yeah, we keep doing this. So this looks very much like the extras, right? That you start from one vertex and then you grow and grow. And what do we need to for every vertex? V in V minus S. We keep the cheapest cost to add it to S. Okay, so initially whatever you can initialize this thing that whatever neighbors of S are, it's just the weight of the edge, that is S to V edge, and then otherwise it's going to be infinity. And then now we use the priority queue. And again, what we need to do, we need to extract min, and then we need to update. And extract min, like just like the extras, will happen n minus 1 times. Update will happen again m times, and update takes log n time. So total time is going to be m log n. So why the update takes m time? Because for each vertex that is being added to S, again we have to look at all the edges, and nothing else can change. Only the neighbor, for the neighbors of this vertex that is being added, things can change, and so on. So because of that, we have the total time will be m log n, because there are going to be total m updates, degree many updates for each vertex to be added, and for all the vertices to be added, it is going to be m, just like the extras. So this analysis is exactly like the extras, and even the data like that, the PQ. Okay, so let's look at Kruskals. So okay, so now we need to implement Kruskal's algorithm. So how do we go about? So first thing is that how does Kruskal's work? It like starts picking the edges in the order of their weight, right? So first it will pick the minimum weight edge, and like add that, then next edge, right? Just a moment. Okay. Now, so first we need to sort edges. That takes m. So if there are m edges, that takes m log m time, but m is order n square, so it is also m log n time. Okay, and then what do? We pick an edge, and then we add it to S or T, whatever the set we have. Then we pick another edge, the next edge from the sorted list, and then we try to add it to S. And we add it to S if this is not creating a cycle. Okay. And if it creates a cycle, then we don't add it to S. So what do we want? Basically, what kind of data structure do we want for this problem? We want that, okay, at every point, we keep this thing, a set of connected components, whatever edges have been added. So suppose this is one connected component, something. Okay. And now we get an edge UV that we want to add from the list. So first we check, okay, so for So what we want to do first, we check which connected component U is in. So there is this operation that we want to support find. Find U. Which connected component or set U is in. To find V to determine connected component or not. So there will be some name that will be placed for the connected component, and then we'll see whether find U is equal to find V. If so, then do nothing. Go to the next edge. The connected components. Right. So basically now, what are the things that we want? So we want basically that we are given some elements of a set. So set, let's say, is whatever V1 to Vn. Okay. And initially, all sets are singleton. Okay, all subsets or all the sets in that in the data structure or in the structure are singleton. And what operations do we want to support? So we want to support basically three operations. Make thing. So it's called make union find. So this operation that I said, this will be the union operation, the merging. Okay. So let's again write it down. So make union find is what is the operation? Initiate the union find data structure. With all sets singleton. Okay. Then what is the find? V return the set that contains V. And then we have union of let's say S1 and S2. And that is merge the sets S1 and S2. So you need to supply the names of the sets, and the data structure will merge those sets. So just like just as I said, if you have these operations, then you can implement Kruskals. So how will we implement Kruskals? It will take for every edge V that is going to be added. It will first do find U, find V, and we'll apply merge the connected components. So how many times this will be applied? So find and will also be applied again. Order n times. Right? Is that fine? So now we'll go and see how to implement this data structure. But all I'm saying is, if we have these operations, if we have support of these operations, we take yeah. Okay. So we have this find operation that will be happening order n times, and this union operation that will be happening order n times.
Excuse me, sir. Excuse me, sir.
Yes, yes, yes.
Sir, actually, your voice is breaking a lot.
Then maybe you can judge it better. But is it any better now, or is it has gotten worse? Okay, I'll switch off my video. Now, is it any better? Or it's the same, or it has gotten worse? Like, at least give me some input, because I can't, measure that.
Sir, it is kind of better now.
Okay, so let's see. If you can't hear anything, please ask me, okay? So I was saying that we need order n union operations and order n find operations for implementing Kruskal's. Because every time, and actually not, so we don't, actually we might need order m times the find operation. Okay, nobody's pointing that out. Because whenever we pick an edge, it might happen that we have to throw it away. So 2 times m in the worst case will end up doing the find operation, right? Is that clear? Is that okay? Will somebody say something? Am I audible?
Yes, sir. It's okay.
Yes, sir, you are audible.
Okay. So, like, is there any question about this? That there will be 2m at max find operations, and there will be n-1 union operations while doing implementing Kruskal's. Okay, if you don't ask questions, I'll just keep going ahead. Fine. So, yeah, so now I'll just go to implementing union find now. And the most basic way to implement it is like, so first let's do an array implementation. So in the array, like for every v in the set, whatever set we have, we keep, let's say, component of v, which is basically tells the set that contains v. Okay. So basically we have this array, and in for every v, so it is indexed by, like, the v, so 1 to n, whatever, and then in this array we keep whatever set contains. So if v is in s1, or v is basically in its own set, so whatever v, let's name it by v itself, the set, and v1 the set, v2 is in v2, and so on, and vn is in v1, because initially they are singletons. And at some point, so this is what we are going to do, though, that we are going to use the names of the elements themselves as sets. Okay. So how much time will find take here? What does find want to do? Find wants to find the set where the yeah. How much?
A constant time.
Constant. It will take order one time. Why? Because you just go to that index and look for the set which is there, and then you output that. You return that. So find V takes order one time. But what about union? Union of, let's say, S1 and S2. That
Minimum
might take,
of the size of S1, S2.
yeah, so minimum of the size of S1, S2.
Order N.
But
Yeah.
yeah, so order N is the max limit. But that is a good point, as Shravan was saying, that we can actually, so order N, why we go and scan through all the array, and wherever we have, so we choose one of the S1 or S2 to be like which one we want it to make the new name of the set, because we basically just want to merge S1 and S2. The names are not that important. So now the new set should contain S1 union S2. So for that, we go through it, the whole array, and basically whichever is smaller, we change that set's name to the other. I mean, we merge that, so other in the array. Okay. So now how do we know that which one is smaller? Requires another thing, size, to be stored. Okay, size of S, let's say, to be stored. So now we have another array, size of S, where S is a set. Again, that is going to be indexed by N only. Why? Because all the sets are going to remain, their names are going to remain from 1 to N or V1 to Vn. Okay, so they are indexed by V1 to Vn. And since the names are going to be the same, the sizes we will get from here. So whenever we get a union S1, S2, then we go to the size thing. Which one size is smaller? We go for S1, we go for S2, and we see which size is smaller. And whatever size is smaller, then we go through the array and all the elements, and then change the ones. So suppose S1 was smaller than S2. Then we go to all the elements where S1 was there and just remove that and put S2 there. Okay. So this is what we are going to do. But again, this also seems a lot, because still for union, in worst case, and what is going to be the worst case? What is going to be the worst case?
Both sets are of size N by 2.
Yeah. So let's say S1 is equal to S2 is equal to N by 2. Okay. We have to, or whatever, N alpha for some alpha less than half. We have to scan, like, whatever constant fraction of the array. Or actually the whole array, because we need to see whether any element, right? Because we don't know. We just know that we need to merge S1 and S2. How are we going to find S1 and S2? We just have the array there. We don't know which elements are there. So then one idea can be, okay, fine, keep the elements also in another thing. In addition to size. So how can you keep the elements? You can have a linked list. So this is like, you can have single linked list, double linked list, but so that you can merge two linked lists in constant time. So now still it is going to be worst case, S1 is equal to S2 is equal to N by 2. But now what we do in merge, just to be clear that what are we going to do in merge? So if we got merge S1, S2, then we go to S1, look at its size, go to S2, look at its size. Then we go for what elements. So suppose S1 is less than S2. Then we go for which elements are there in S1, which is a linked list. And then for all those elements, so suppose here there was vi. Then for that element vi, I go to the array, I look at vi and change its set from S1 to S2. Then I go to the next one, whatever vi plus 1, let's say, not vi plus 1, vj, whatever. And then I go, so that is the next element of S1. And then I change that. Then I go and change that to S2 and so on. Okay. And finally, what I do, so I put this head of, I merge these two linked lists to the one which is there at S2. So S2 points to whatever its linked list, S1 points to its linked list. So what I'm going to do, I'm going to merge this. So I'm going to put this in front of that here. So I'll put the pointer basically to the head of S1's list. Okay. So I take the S1's list and I put it in front of S2's list. So at least the procedure is clear that what we are doing. Any questions about this? So we are storing three things now. For we have an array, that is the component array. For every element, we know we are storing which set it belongs to. And for every set, we are storing two things. We are storing its size and we are storing all the elements there. So now find is still the same. Find is still order 1. But now for union, what we are doing, for union, we are going to the sets, then looking for which set is smaller. Whichever set is smaller, then we go for the elements of that set and change the entry there and also merge the elements of both the sets in the larger set. Is that clear?
Yes, sir.
Okay, good. Thank you. Yeah, please respond, because when I ask, is that clear? I generally ask that where I have certain doubts that, okay, maybe something might not have been gotten across something or very clearly or something like that. So when I ask that, if somebody can reply, it will be very helpful for me. Okay, good. So now let's do a running time analysis. So of course, as we saw that find is order 1. And union is order n in the worst case. And worst case is smaller set is still order n. Or sorry, not order n, omega n. The smaller set is still big. It is still at least a constant factor of n, right? So, but the question is, can this worst case happen too many times? And the answer is no, that actually on average, we will not need to spend so much time, order n time on union operation. So what the lemma will say in this implementation, a sequence of k, let's say, union operations will take order k log k time. Okay. So any ideas why or how we will approach this? So on average, this is only taking k log k time. While earlier we said that one can take omega n time. One can take order n time, so maybe it should be kn if we were looking at that. But now we are saying that it will be k log k. So how do we get this decrease? So again, the implementation is the same. We are not going to change the implementation. We are just going to analyze things a bit better. Okay.
Here we
So
change the label.
yeah, it's not very trivial, but once you
Hello.
yeah, we are changing the label.
Yeah, no, I'm
Yeah.
saying we change the label of
Yeah,
each
we
element
are
at
changing the
most log
label
and
in
k.
the. We change the label of each element at most log n times. That's correct. So yeah, let's do that slightly formally. So if we have a sequence of k operations from beginning, how many elements it can affect? So tell me, how many elements it can affect? A sequence of k operation. How many, so if I draw a graph, so suppose initially the graph is all singleton vertices, and then we start making, merging them, or, at one time, I can put one edge either between two connected components or between two vertices. Because that is what is happening in some sense. So how many vertices? How many vertices are not singleton anymore? Can we give an upper bound for the vertices which are not singleton anymore after k operations? No? Am I audible? I mean, I expect an answer for this one.
Okay.
Again, Anshuman? Sorry?
I think it should be n minus 2k.
N minus 2k. Actually, I'm saying how many can get affected?
So
Or
2k,
yeah, at
like
most
upper
2k
bound
can
would be
get affected.
2k and
Yeah,
lower bound should be order k, I guess. Like around
yeah,
k.
but the lower bound, we just need the upper bound, okay? So at most 2k vertices can get affected. Vertices labels can change. And what is the size of the largest set? Is again order k. I mean, any new set, the one which has not changed. So largest set, yeah, that is fine. So these are the things that at most 2k vertices labels can change, and the size of the largest set is also order k. And whenever a vertex label change, vertex's label changes.
Excuse me, sir.
Yes, tell me.
How will 2k vertices label be changed?
Again, I mean, labels can change. Okay, not labels can change, can be affected by this operation. The labels maybe k vertices. Yeah, labels will not change for more than k vertices. But at most 2k vertices are affected, so at most 2k labels can change. I mean, but again, this is an upper bound, right? So that is, it might not be that 2k labels can change, but we are fine with order k. Okay. So the point is that whenever a vertex label changes, the set that it belongs to grows by at least double. And why does this happen? Like a factor of 2.
We're changing the label for the smaller set. So
Yes. So we are changing the label for the smaller set. So that's it. So, but let's just put things together. So since the size every time the label changes, and at most the size can grow to order k. So for one vertex, the number of label changes is at most log k, order log k, basically, yeah, whatever. And now, how many vertices for which labels can change order k? So total number of label changes for all vertices is equal to order k log k, right? And this
So
is the
shouldn't it be log n and not log k?
why it should be log n, because we just said that for one vertex the number of label changes is log k, and there are at most order k vertices whose label can change in. So total changes for all vertices in k operations.
Oh, okay.
So the lemma that we had was for k union operations. Okay. So again, we will replace it by n or whatever, but this is true for any k. Okay. So then we get k log k many, and then this is the more expensive thing. This is the only expensive thing, because for every union operation, everything else is constant time. What else we do for union operation? We go and look at the size. Looking at the size is constant time. Then we go and merge these two lists. They are linked lists. Merging them is constant time. The only thing that was taking more time was the label thing, and the label thing we have shown is order k log k. So now the union operation can be done in order k log k time for sequence of k operations. Okay, so sequence of n operations, order n log n. Okay, so let me just quickly. So this is, I think, still fine for, and also for the find. So we had m finds, and for the find we have order one time. So that is m time. And yeah, so I guess this is fine. So total time then becomes for this thing order n log n, which seems a bit strange. Okay, let me check with the book, because there's something strange there. Just a moment. No, this is all right. Yeah. So actually, so it can be done in order n log n time. So the book later says m log n, but I don't see why that has to be the case. I think it should be n log n. So you guys can have a look at it later and let me know. I think it should be n log n, total time taken for Kruskals with this approach. Okay.
Should be m plus n log n, right?
M plus, yeah,
So
sure.
sorting takes m log n.
Sorting takes m log n. Good. Thank you. Sorting takes m log n. So that I had forgotten. So total time is order m log n, because sorting takes m log n. So sorting is the bottleneck. Thank you. Good. So fine. So this was for this particular data structure, but now there is another improvement of this where we can actually, so
Sir, for the array, sir, we are storing, for each vertex, we are storing which component it's part of, right?
yes, that's correct.
So when we are changing the values of the set that convert component 1 to component 2, then we have to traverse all the array.
Yeah.
case.
No, you don't have to traverse all the array. We are keeping another thing, right? For each set, we are also keeping the set of elements in a linked list. Okay, so for each set, we are keeping two things. We are keeping its size and we are keeping all the elements in it. So whenever a set is referenced, we go and find its elements and we only go and change there. So we don't have to traverse the whole array. Does that answer your question, Avdesh?
Yes, sir.
Okay. So improvement, what we want to do now? Now we want to bring the worst case thing down. Worst case of union from down. Okay, so let's see how much down we can bring it. And we'll do it at the cost of increasing the time for find. Okay, so now instead of an array, what we are going to do, we are going to have a pointer based implementation. So now for each vertex, let's say, we have a record which can be placed in an array. But what does that record contain? The record contains a link to the set that it belongs to. Okay. And now we are like sort of going to exploit this thing that the set names why are we sorting the linked list if we do not use them for find? We are not sorting the linked list. We are sorting the edges according to their weights because Kruskal wants to consider the edges according to their weights. Mrityunjay, does that answer your question?
Yes.
Yeah, so we are storing linked list. We don't use them for find. Yes, but we use them for union, right?
Yes, I got it.
Yeah, okay, good. So, all right. So now for every V, what we have is a record. Okay, and that record contains a link to the which set it belongs to, right? So now, and again is the same. So now it's a record, and this record is empty initially because it does not point to anything. And suppose now U and V are there, and we want to merge these two sets, U and V. So what we'll have that, okay, we'll put a link to this record, to the record of V, which basically, or if the whole thing, so the record contains V and the link, then we will put a link to this whole thing here now. So there will be a link that will point to. So basically, now what happens is that for union, you don't need to do anything. Union, you just go to that set, and so that set, which is basically name of an element. And put a link to the larger set. So again, we are going to follow the convention that if U and V are going to be merged, so you want to do union of U and V because now U and V are going to be the set names, let's say, then we will again merge the, put the link of the larger set into smaller. Got it, okay? So now it's like, it might seem like a strange thing that what is happening here, how can we union two sets by just doing pointer change at just one element? Because that is the element which is the name, right? So for example, so suppose there is this W which is there. So this is the figure in the book that I'm copying. So suppose W got merged to U first. So there is this record that points to U. Then S also got merged to this U. Then first what happened was there was this set T and Z, and then they got merged to V. So they point there first, and then this set U got merged to V. So then I put a pointer from U to V. Okay. So now this is what the operation does. And so now how much time does union take? Union take constant time. Why? We just go to those records and put link of one record into the other. So union takes order one time. But what about find now? How can we do find? In this data structure, how can we do? How will we do find?
If we don't compress the paths, then it is going to take us linear time to go to the representative of the set.
Yes, but okay. So, yeah. So, but how do we go to the representative of the set? We just follow the pointers.
We just follow the pointers up until the pointer points to itself.
To itself or empty, yeah, whatever. So there can be some convention that where the pointer is to itself or is empty, and that is the set that contains that element. Okay. Now again, but what we want to show, let's say that lemma says that for a sequence of, or let's say that that it can only be log n, that find V takes order log n time. So can somebody tell the proof? So it will not be linear.
Again, we will be like making the smaller set point to the bigger one.
Sir, we can
Representative
say
of the smaller
that
set.
height
Exactly.
of this tree.
So again, we are having the convention of making the smaller set pointing. Yeah, height of this tree. So again, instead of going into these things, let's just say that a pointer is changed. Only if in the previous implementation, the label will be changed. Right? And how many times a label can change? At most, because the set size can be at most n. So how many times the label can change? At most log n. Is that clear?
Yes, sir.
Because this is exactly analogous, that wherever we were changing the label, now we are just changing the pointer. There's no difference. So how many times a pointer can change, or how many actually, yeah, how many times we have to traverse the pointer? Actually, not pointer can change. We have to traverse one more pointer for every label change. So if you look at the figure, then you can that okay, first time W's pointer changed to U, then its label got changed, right, to U. So there was this record for W, which initially had just W, and then first time it got changed, we changed it to U in the previous implementation, and then pointer also changed. Then we put this whole set U also, we merged it with V. Then we come and change the record to V, and then for that we have to traverse one more pointer now, right? So number of pointers that are being traversed is the number of times the set name will be changed, not the number of times the pointer is changed, right? Okay. So that's why this is going to be at most log n. So here again, the find operation takes log n, and there are m find operations in Kruskals. So this takes order m log n. The sorting also takes order m log n. So total time is order m log n for Kruskals. Okay. So this was the union find data structure, and as Mani was suggesting, we can compress these pointers also. That okay, once W is accessed, then once we follow the pointers, after that we can put a direct pointer, and we don't really need to go through this and all. And when you so there is a way to analyze that. We are not going to do that here. And then what turns out that actually a sequence of n find operations will take n alpha n time, where alpha is inverse Ackermann function. Which is something like, grows very slowly, much slower than log or something, almost a constant. So for all practical purposes, the book says that its value is less than or equal to 4. So again, and how this is achieved? By compressing the pointers. That okay, if you're going to make a reference to an element again and again, then why always go through this path? Once you make the axis, then as well change the pointer there and keep the pointer directly to. In fact, for all the once you make the axis, then for all even the intermediate things, you can keep the pointer to the next thing, so that for them next time you don't have to spend anything. You can just in one step do that. Okay, so that can be done, and that makes it even faster. But that does not really improve our running time, because the sorting is a bottleneck in running time, and sorting itself takes m log n time. Okay. There is another problem which I wanted to do, but we lost some time, which was clustering. But let me just quickly tell you what the problem is. You are given a set of points, and they are not necessarily in a plane, but you are given a distance metric such that it is symmetric, reflexive, and d of p1 and p2 is non-zero if p1 and p2 are not equal. And what you want to do, you want to put them in k clusters. So you want to put them in k groups. So C1 to Ck, such that the distance, the minimum distance is distance between points in different clusters is maximized. Okay. So this is what you want to do, and the algorithm for this is actually very simple. So basically what you want, so this is called spacing. That if you look at 2 points in different clusters, their distance should not be very less. It should be a long distance. So that's what you want to maximize, and for that the algorithm is just find MST, where edge weights are distances, and delete the most expensive edges. Most expensive n minus k plus 1 edges. So it has n minus 1 edges, or n minus 1, yeah, I think so. So then it will have k connected components, and that will be your answer. Or otherwise, you keep doing your this Kruskals and stop when you have k connected components. So you keep adding the edges one by one. So those points which are closest, you keep putting them in clusters. Okay, these two are closest. Okay, now these two are closest. So fine, they become one cluster. Two are closest one, and you stop when you have reached k connected components. So you can look up the proof, or you can try proving it by yourself, and I think it will be a nice exercise. Okay. So that's it for today. Actually, yeah, we are over time. So this is a problem which is like, actually it's quite simple if you have the algorithm at least. And then you should have a look at the proof. And the basic thing today I wanted to cover was union find. And I think I did that. So any questions about union find? So there are two implementations that we saw. And in the second implementation, I just that how more things can be done. Any questions? Okay, so if not, then thank you. And yeah, we'll see you on Tuesday. Thank you.